Hello everyone! In this video we will talk about the electrical characterization of plasma sources used in the agri-food field. This video is funded by the European Cost Action Plasma Applications for Smart and Sustainable Agriculture. Let's start this video by answering to a fundamental question. What does electrical characterization of plasma sources mean? Electrical characterization means investigating the behavior of plasma source from an electrical point of view. To do this, it is necessary to create a so-called electrical characterization setup, namely an assembly of components which contribute to analyze our plasma source. This kind of setup is typically composed of a plasma source, a power supply, several electronic probes, an oscilloscope, and a software to process the acquired data. All these elements will be described in detail in the following. The core of the electrical characterization is the plasma source we would like to study. There are many plasma sources which are typically used in the agri-food field. The most common among them are reported in this slide. There are dielectric barrier discharges, which are made of three components: a high voltage electrode, at least one dielectric layer, and a ground electrode. The plasma discharge is generated in the gap between the dielectric layer and the ground electrode. Then, there are surface dielectric barrier discharges. These sources are made of the same three components of the dielectric barrier discharges, but with the difference that the ground electrode is in form of a mesh, and it is directly in contact with the dielectric layer. In this case, plasma is generated in the holes of the mesh. Finally, there are jets. These plasma sources involve a flow of gas which is ionized within the source and then pushed out by the gas itself. The high voltage electrode is always present in these sources, while the ground electrode can be a component included in the plasma source or the substrate to be treated. In order to ignite and sustain a plasma discharge, the presented plasma sources need to be connected to a power supply. The number of commercially available power supplies is large. There are direct current power supplies which can be characterized by constant high voltage or pulsed high voltage. But there are also alternating current power supplies. In this case, signals can be, for example, sinusoidal or pulsed. For AC signals, we can distinguish the power supply also based on the operating range of frequency. In fact, we can work in the audio frequency, radio frequency, or microwave range. Depending on the plasma source, and of course on the application, a proper power supply needs to be selected. For example, the working principle of dielectric barrier discharges exclusively matches with AC power supply. To analyze the electrical behavior of the plasma source, it is necessary to add electronic probes to the circuit. The high voltage probe measures the voltage difference between a metallic contact on the high voltage cable and the ground. A good contact between the probe and the circuit is fundamental to accurately measure the voltage. The current probe is placed around the cable and measures the current by sensing the strength of the electromagnetic field produced by the current flowing through the cable. The current probe can be substituted also by a Rogowski coil or by the combination of a known resistor and the voltage probe. The location of the probes in the circuit strongly depends on the plasma source which we would like to characterize. For the electrical characterization of a simple dielectric barrier discharge, the high voltage probe is typically located on the high voltage cable, and the current probe on the grounded cable. The same configuration of probes usually well fits with surface dielectric barrier discharges and jets with a well-defined ground electrode. In some cases, for example for sources which have a poorly defined ground electrode, it may be beneficial to measure the current directly on the high voltage line between the power supply and the plasma source. This poses additional safety challenges, since unwanted discharging between the high voltage cable and the current probe must be prevented. The electronic probes are connected to an oscilloscope, an instrument which graphically displays the electrical signals as a function of the time and allows to save them. By observing the acquired current and voltage signals, numerous information about the electrical behavior of the plasma source can be derived. For example, we can recognize the so-called peak voltage, which is the maximum value, positive or negative, of voltage, or the peak-to-peak voltage, that is the difference between the maximum positive and the maximum negative voltage amplitudes. When we have AC power supply, we can easily also distinguish the period, which is the time interval required for the waveform to repeat itself from start to finish, and the frequency, which is the inverse of the period. But it's not over. There are other useful information which can be obtained by giving a look to current and voltage waveforms. For example, considering the current waveform, the presence of passive and active phases in the working principle of the plasma source can be distinguished. Let's suppose to characterize the electric barrier discharge. We can notice the presence of passive phases by the absence of spikes in the current waveform. In fact, in that moment, the plasma discharge is off, and the measured current is equal to the displacement current, namely the current which is generated when we apply an electric field to the plasma source. If we further increase the voltage provided by the power supply, the breakdown voltage can be reached, and the plasma discharge can be ignited, giving start to the so-called active phases. During active phases, the measured current is the sum of the displacement current and the discharge current, and we can observe spikes in the current waveform. From the current and voltage signals saved with the oscilloscope and using appropriate software for data processing, we can also calculate the power dissipated in the discharge averaged over the voltage period T. Using the conventional method, which well applies to all the plasma sources, the discharge power can be obtained as the integral over the period of the product of the current and the voltage multiplied for the inverse of the period, which is the frequency. But there is another method to calculate the power dissipated in the discharge, which can be used mainly for the electric barrier discharges driven by sinusoidal signals, the so-called Lissajous method, also known as a QV-plot method. In this case, a modification in the electrical characterization setup must be performed. The current probe must be replaced by a capacitor of known value, often called monitor capacitor, and by a low voltage probe. A good choice of the monitor capacitor allows to calculate the charge flowing through the plasma source as a product between the capacitance value and the voltage measured by the low voltage probe. By plotting the charge as a function of the applied voltage, the so-called Lissajous figure can be created, and its area, multiplied for the frequency, can provide the value of the average discharge power. As you could see from this video, the information which can be obtained from the electrical characterization of a plasma source are numerous and can be very useful for our activities. First, knowing the electrical characteristics of a plasma source and the related dissipated power may help in the development of the process where the plasma source is involved. Let's think about the production of reactive species for the decontamination of packaging surfaces using surface dielectric barrier discharges. The power density is a fundamental parameter to find the proper chemical regime to maximize the decontamination effects. Then, electrical characterization can be beneficial to evaluate and compare plasma sources' performances. Through electrical characterization, for example, we can know how many reactive species in the plasma-activated water we can produce given a certain electrical consumption, or again, compare the results with those obtained by another lab in the COS community. Finally, the information from the electrical characterization are valuable to guide the upscale of processes from our laboratories to the industry. In conclusion, electrical characterization represents a powerful tool in the frame of the European cost action, Plasma Applications for Smart and Sustainable Agriculture. Thank you for watching this video.